Let's wait for 2 3 minutes. After that, I will start. Let's start. So this is the last week. This is week 13, problem solving session. It's regression analysis. So today, my plan is that at the very starting, we will talk about the assignment questions, definitely. The assignment questions of week 12. And once we finish this, one of the concepts was not covered last week. That is that nonlinear models or nonlinear estimation. We will talk about this, the regression of the nonlinear model estimation. So this we will do after that. And once we finish this nonlinear model estimation, just giving a brief introduction of that. After that, we will move towards solving some questions based on simple linear regression and multiple linear regression model. Because as we have seen, so many weeks we have devoted to this particular uh, this regression analysis, and we have seen that in almost all the weeks you have used either simple linear regression or multiple linear regression. to solve a particular question. So it's important to just revise again the questions which are associated with simple linear regression model and multiple linear regression model, because this is the fundamental thing. Based on that, there are different things. So we will see that after we finish the first and the second part. Okay, so this is today's plan. Let me switch off the video now. Okay, so let's start with the assignment questions. Week 12. Okay, so let's go to the questions. Just a minute. Right. So the first question is, suppose you have n observations of variables x1 to xk, there are k regressors, you can see, and there is a y where x's are regressors and y is the response variable. Suppose y's are binomial ratios, that is yi is equal to ri by m, where m is a constant and ri is the number of successes. We consider fitting the model like this. Then what is a reasonable choice of f of y? When we know that from the last class that this yi is equal to ri by n, this kind of things we have seen in the binomial kind of a distribution, right? So it's coming from the binomial distribution, right? So this we have already seen in the last lecture. Okay, so where m is a constant and ri is what you call as the number of successes. So actually, it is now becoming that m, the total number, cr, that is, it's a combination kind of a thing, and then you will have some probability of success, p to the power r, that is the number of successes, and 1 minus p to the power m minus r. This is how the distribution looks like. And then you can reduce it to this mcr, then p upon 1 minus p to the power r, and finally 1 minus p to the power m. This is how you can also write. So we have seen this. Now the reasonable choice when you are writing this kind of a distribution, if and consisting of this y variable, and you are writing this f of y is equal to some beta 1 x1 plus beta 2 x2 and so on up to beta k xk, then you should know that since it is a binomial kind of a distribution and which belongs to an exponential family, this f of y should be a kind of a link function, right? And we know that the link function corresponding to this binomial distribution, which is nothing but the natural parameter theta, that is b of theta, is, we have seen, for this is for binomial kind of a distribution. If this y's this are coming from binomial distribution, then you know that this b of theta, which is equal to p, the probability of success, is log of p upon 1 minus p. This we have found when we have fitted this into an exponential family of distribution. There we have found out this. Now, since y's are coming from this, it's a function of y. Instead of writing log p upon 1 minus p, we can directly write the link function f of y as log of, just replacing p with y. This should be your link function, correct? Because we have seen that the link functions are nothing but the natural parameter. B of theta is the natural parameter, correct? So the reasonable choice for this kind of a distribution, the binomial kind of a distribution of this fy, if you are fitting the model like this, then f of y should be log of the probability of success coming to y upon 1 minus y. So this should be the correct answer for the first one. Okay. So if you will look into this, C option, the third option, log y upon 1 minus y, is the reasonable choice of the Ling function f of y. Okay, so this is done. Next is consider the density function with parameter p, where it is given that f of x comma p is 1 minus p to the power x minus 1 into p. For k goes like this. Is this density a member of exponential family? Well, let's see whether it is of exponential family or not. So what is that function? Let me write f of x comma p, where x is some kind of a random variable, p is some parameter, and this is 1 minus p x minus 1 into p. Question is it belonging to an exponential member of distribution? Let's see. We know that we start with to check whether it is a family, it is falling into the family of exponential member of distribution. What we start with, we just directly write exponential and try to reduce this function in terms of exponential function. So how you can write? Take log. That will be the best thing because exponential and log will cancel. So it will be log of 1 minus p to the power x minus 1 plus log of p because it is in multiplication. So if you take log, it can be easily written like this. And if you just open this particular thing, so you can see that exponential and log cancels out and you get this back, right? So let us write exponential. Further, we can reduce this to this. This is the property of logarithm, you know. So this is log of t. That's all. Third, what we can further reduce? Exponential x into log of 1 minus p minus log of 1 minus p plus log of p. Right? So yes, we can see that yes, it can be reduced. It is falling under the exponential member of distribution, right? Because we can write this particular function in terms of this exponential function, right? So that's why we can. So if you further look into it, you can check for the parameters like a of x because I'm writing x because that is the random variable. So a of x is, look at this term. This is x. B of natural parameter, b of theta, the parameter p is log of 1 minus. This is coming from the first term. And there will be a c of p, which is nothing but log of, you can combine these two as p upon 1 minus p, and d of x is 0. Nothing is there. But still, it is an exponential member of distribution. So yes, the answer is yes. We can write that particular function as, yeah. So you can write this particular density function as a member of exponential family. So yes is the correct. Okay, let's go for the third one. Consider the density with parameter theta. Now this is another function which is given. Is this density in canonical form? This is the question. So before going to the canonical form, we have to first reduce it into the exponential member of distribution. Okay. So let's go to the third question, where it is being asked that this is the function which is given to you, x comma theta, where x is the random variable, theta is the natural parameter. This is theta x to the power minus theta plus 1. So x is greater than equal to 0 is the condition for this particular density function. First is to understand whether it is in canonical form or not. You have to go ahead for reducing it into the exponential distribution. So let's see whether we can reduce it or not. Take log again. That's the best possible thing which we have. Log theta plus log of x to the power minus theta plus 1. That's all. Next, exponential, write it as it is. This is log theta. Further, we can reduce this. So this will be minus theta plus 1 log of x. Right? Next, this will be exponential log of theta minus theta log x minus log x. Right? This we can finally write. Okay, just look at this particular term. It consists of both a parameter theta and a function of some x, the random variable. Therefore, from here, we can calculate what is ax. Ax can be written as log x. B of theta is minus theta. C of theta is log theta. And D of x is minus log x. So it is definitely a member of exponential family or exponential member, right? But question is whether this particular density function is of a canonical form or not. To understand whether it is of a canonical form, the condition for canonical form is that a of x should be equal to x, right? This is the condition for canonical form. So are we getting a canonical form? Well, a of x comes out to be log of x, which is not equal to x. Therefore, it's not of a canonical form, right? So no should be the answer corresponding to this particular question. So if you go to the question, yes. For the third, it is no. Okay. Let's go to the fourth question. It says that consider the density function with parameter k, and this is the density function which is given. Is this density function a member of exponential family? This is the question. So let's see. So the fourth one is that you have f of x comma k, which is the density function given. Let me write it down. 2 to the power k by 2 gamma of k by 2. So you can see that it's a gamma function or it's a gamma distribution x to the power k by 2 minus 1 and finally e to the power minus x by 2 where x should be greater than equal to. This is the condition. This is the gamma distribution you can understand from the way it is written. So again, whether it is falling into the exponential group of distribution or not. For that, you know the starting point is that start with an exponential bracket and try to reduce the entire function. Best is to take log. Okay. But see this term. This already consists of exponential. So you can directly write minus x by 2. First term. Other things you can try using log. So you can write log of x to the power a by 2 minus 1, the numerator term. Denominator term you can write like this a by 2 minus log of gamma k by 2. That's all. You can reduce it into an exponential distribution. So, but let us reduce it further. X by 2. This becomes k by 2 minus 1 log of x, and finally you get log of 2 to the power k by 2 minus log of gamma k by 2. That's all. So yes, it can be reduced or it is falling under exponential family, which we have seen also in the gamma distribution. It happens to be a member of exponential family. Okay, so this is the so fourth question. If you see, yes, it is a member of exponential family. Go to the fifth question. What is the natural parameter? Okay, so as you can see here, this is in totality which is there. So for the fifth one, you can see that this is the multiplication term, right? So you can write that b of theta or which is equal to b of theta is equal to k is nothing but k by 2 minus 1. So this is the natural parameter. Okay, so this is the natural parameter because this is the term from which we are going to find out the natural parameter. Okay, so this is what the uh, natural parameter looks like. That's all. Okay, come to the sixth question. So natural parameter we have seen as k by 2 minus 1. Okay, now sixth is suppose you have n observations of variables with where x is at the initial, y is the response variable, and y is coming from the Poisson variable. We consider fitting a model like this. Again, the reasonable choice of f of y. So whenever you are writing having y as coming from some kind of a distribution like Poisson distribution other than the normal distribution, because our assumption is that y should come from a normal distribution, just like the error term. Error term should come from a normal distribution. Similarly, y should also come from a normal distribution. But if it is not a normal distribution, then we use generalized linear model where we write f of y is equal to like this as the model, where f of y is some kind of a link function. And for Poisson variable as y, the link function is as we have discussed. So for Poisson distribution, the link function is your f of y. So f of y, which is equal to log of y. Why? This is because if you remember, the natural parameter b of theta is equal to say mu is log of mu in case of Poisson variable or Poisson distribution. So this is from the last. Okay. So this is done. Next is the seventh one. Seventh is the negative binomial probability mass function is given like this. Here the natural parameter is. So this is directly coming from the question. You can start with whatever it is written. So negative binomial distribution, which is given as f of x comma p is x plus r minus 1 p x p to the power r 1 minus p to the power x. Right. So just reduce it into the exponential function. So it becomes log of x plus r minus 1 px plus r log p minus x log 1 minus p. Okay, so we can write them as you can see. Now here your x, so a of x is x. Okay, so you can write your b of p, that is the natural parameter, minus log of 1 minus p. You can write it like this. Okay, so or so look at the options which are available. So you have p, log 1 minus p and 1 minus p. So what you can do is that since you have a minus sign over here, you can take this as minus x, it does not matter, and you can take this as a plus. Okay, so the natural parameter as per the options which are given is log of 1 minus p. Okay, just fit it into an exponential function, exponential number, and then you try to look for that particular uh, product of the functions where you have something of a function of x, something of a function of a natural or some kind of parameter, particularly the parameter of interest. Like here, r is the nuisance parameter, right? So this is done. Let's go to the last question, eighth question. In the eighth question, It is asked that suppose you have n observations and like the same way, same questions, but y now is a normal variable. So it's easy for us. You know that our all assumption stands where y is of normal distribution. When you know that y is coming from a normal distribution, you know that we have done so many things. Right? We can write y is equal to beta 1 x1 plus beta 2 x2 plus so on up to beta k. We have seen this. We have used multiple linear regression model based on this particular assumption. So it's sure that if y is coming from a normal distribution, then your f of y is actually equal to y. So here f of y should be equal to 1. But if you want to go from that exponential member of family of distribution, you should remember that v of mu, the natural parameter in this case, natural parameter is mu upon sigma square, where sigma square is an instance parameter, right? So it's not of an interest. So it's only depending upon mu. Therefore, you replace mu with y. So replace mu with y, and you get your f of y is equal to y. So in both ways, you are right. Okay. So just this is what our assumption is, that epsilon is a normal distribution with zero mean and sigma square variance, and y should also follow a normal distribution in case of a multiple linear regression model or simple linear regression model. Okay, so if y is coming from a normal distribution, we can definitely write it. So therefore, the reasonable choice is f of y is equal to 1. So with this, we I think came into the end. So this is the accepted answer y. Okay, so that's all. This is the week 12 assignment. We have solved all the questions. So it's based on completely on the exponential member of distribution, canonical form, and the generalized linear model part. Okay, so we have discussed most of the things. So this is done. So next, let us go ahead with the nonlinear estimation. Okay, so we will do this nonlinear estimation. I will give you a brief concept because that is not being covered. I couldn't cover in the last class, so I will try to do it today. And after that, we will practice one simple linear regression model question and another multiple linear regression model question. So that will clear up most of the concepts. Okay, so let's go for one of the week 12 contents, which is not being covered in the last class. That is the non-linear estimation. Okay, so I will briefly cover this. So models that are non-linear in parameter. Okay, that is where this non-linear estimator comes into play. For example, y is equal to, as given in the week 12 lectures, you can see theta 1 plus theta 2 t plus epsilon. See, exponential function itself is a nonlinear function, and you can see that the parameters here, the parameters are here theta 1 and theta 2. T is the regressor variable. So here, in case of nonlinear estimation, there is a change in the symbols. I will discuss it later, or if you have gone through the video lectures, you will find out that the t, this term is represented as the regressor, and thetas are represented as the parameters. So when you find that a model is created where the parameters are in non-linear kind of a fashion. The particular function is of a non-linear fashion, non-linear function of these parameters. Then we can go for a non-linear estimation technique. Another example is suppose this y is equal to some theta 1 divided by theta 1 minus theta 2. This is exponential minus theta t to the power minus theta 1. That's all plus epsilon. So this is also a kind of a non-linear kind of a function in thetas. Okay. So I will let me write that here where t is regressor variable, regressor variables you can say, and theta are parameters. Right. So this is how the nonlinear estimation is defined. That this is how the models of nonlinear models are defined. Okay. So this equation, the equation which mentioned above, the equations mentioned above are nonlinear in the sense that they involve parameters theta 1 and theta 2 in a nonlinear way. You can see that clearly, right? So you can see that this function or this function, you can see that the theta 1 and theta 2, these are a nonlinear functions. This y is in some case associated with theta 1 and theta 2 in some kind of a nonlinear function, right? So this is what we mean by the nonlinear estimation. Okay, so now suppose you have another example, say the first one. Suppose you look at this one. Okay, if you take log, so let us say that this is the first. Okay, so equation one, if you look at what is given, y is equal to e to the power theta 1 plus theta 2 t plus epsilon. Right? So now if you take log, so log of y will be nothing but theta 1 plus theta 2 t plus epsilon. So you can write this as y dash and this as some a kind of an x. So it's kind of an intrinsically or intrinsically linear model. Okay, this kind of a model is intrinsically linear, where you can just change one variable slightly, taking some logarithm or something like that, and you can reduce it into a linear form. That is intrinsically linear. That is, it can be converted to linear form. All right. Okay. Now let's look at the symbols. That is, you have your linear regression model and non-linear estimation or non-linear model. Okay. So first is the response variable. Let's response. For the linear regression model, the symbol is 1. In the non-linear model, also the symbol is 1. Second, regressors. We know that in the linear regression model, it was x, right? x1, x2, x3, up to xk. So you can write like that, x1, x2, so on, up to xk minus 1 we have written, always. And for the non-linear case, it will be t1, t2, so on, up to tk minus 1. Third is the parameters. What parameters we have used in case of linear model? They are beta. You can start with naught, beta 1, so on up to beta k minus 1, right? Where beta naught is corresponding to the 1 value. And in case of nonlinear estimation, it starts with theta 1, theta 2, so on up to theta k minus 1. That's all. So these are the symbols which we use for a nonlinear estimation model and the linear regression model. Okay, these are the difference in the symbols. Okay, so let's write therefore the y in case of the nonlinear estimation can be written as a function of all the regressors like t1, t2, so on up to say tk and theta 1, theta 2, so on up to let us consider theta p. That is, there are p parameters and k regressors. So some kind of a function where this kind of changes can be done. Okay, where now t tilde is a t vector. So you can see that what if I write now first t2 up to say tk transpose. This means that so there are k number of regressors. Okay, k regressors. Okay, k regressors with some n observation. Okay, so it is actually a if you look at it has some rows as well as columns. So it is written as some kind of a transpose. That means it's kind of a it's kind of a row matrix, but each of these T1, T2, and Tk has n observations. So it will be a large row versus column matrix. Okay, so we have written it in kind of a vector form. Well, next is the theta that can be also written as some kind of a vector, such as this theta 1, theta 2, and so on up to theta p dash, or means the transpose. Okay, so this is kind of a vector form. But here, okay, this theta 1 will have only one value, like we have beta naught, beta 1, beta 2, like that. Okay, therefore, based on this, we can further reduce the y is equal to f of the regressor matrix or vector and the parameter plus xi. This is now the nonlinear distribution model. You take expectation of y, that should be f of t tilde theta tilde and plus 0. Why? Because we always assume whether it is a linear or a non-linear model, E of epsilon we assume to be 0. This is the assumption which we have always taken in case of linear regression model also. Okay, assumption is that epsilon coming from a normal distribution with zero mean and sigma square constant variance. Okay, so this is the concept. Now, suppose I have already given a hint here earlier. So suppose we have n observations. So u suppose is going to 1 to. So what we generally write as I is equal to 1 to n in case of linear regression model. Here we are denoting some kind of variable like u. Okay, so it will be some kind of y of u. That is this y, this response will have u observations. That is n observations will be there, and there is a tu tilde, that is each of the regressor variables will have n observations. Okay, because you know that this t tilde is this, so there are k regressors but with n observations. I have already written it here already. Now it is much more clear that tu represents that for each and every regressors t1, t2, t3 up to tk, there are u observations. Means u goes from 1 to n. Okay, so this is how you can write. Further, it should be y of u, f of c, t tilde u, comma, theta tilde plus epsilon u. Clearly see that theta tilde does not have u because theta does not depend on the observation. It's a parameter. Okay, fine. So this is your final nonlinear estimation model, general expression. Now, if you try to go ahead with the same way as we go for the linear regression model, you go for what? You go for error or residuals, residual sum of square, SS residual, what we call residual sum of squares, right? So we can write S of theta as summation yu minus f of tu tilde theta tilde and whole square. This is what we do. Generally we do. And this should be in U, remember. Okay, so this is already done. Now what we do? To find, same way we will proceed as we go for the general regression models, linear regression models, to find the least square estimates of theta hat, we need to differentiate S theta with respect to theta tilde. And we have P normal equations. Definitely. Why? Why there are P normal equations? Because there are P number of thetas. Remember this. There are P parameters. Therefore, there will be P number of equations. Just like we have, say, let us consider y is equal to beta naught plus beta 1 x plus epsilon. So, beta naught and beta 1 are two parameters. Okay, so beta naught and beta 1 are two parameters. Now, if beta naught and beta 1 are two parameters, you remember that whenever you do the SS residual, sum of square residual, you get two normal equations, correct? And with these two normal equations, we find out beta naught hat and beta 1 hat. Similarly, if you have p parameters, then there will be p normal equations, just like that, same way. Okay, so now, only thing is that expressions will change. For example, if we do the same thing, we differentiate s theta with respect to theta tilde, it becomes like this: yu minus f of u tilde theta tilde whole square. No, the square will not come because it will be differentiated delta f by delta theta I tu tilde theta tilde. Okay, and theta I is equal to theta I hat. This should be equal to 0. Okay. Now, what is this I? This I represents the ith parameter. Remember, I goes for 1, 2, 3 to up to p. Remember, so I represents the ith parameter, right? So it will be differentiated with respect to theta 1, theta 2, theta 3 up to theta p. That's how it will be differentiated. And that value where it becomes 0, that expression where it becomes 0 will be the one of the normal equations corresponding to that ith parameter of theta. Okay, so this is how you can understand. Okay, so here there are some criteria. Here this f tu tilde theta tilde is linear. Okay, and delta f by delta theta I is a function of tu tilde and independent of theta, theta I theta. You can write. Okay, let's come to the next part. That suppose when the model is nonlinear in theta, our normal equations also becomes nonlinear. Also becomes nonlinear, which is what we are trying to estimate. Okay. So this normal equations becomes nonlinear. How? Suppose y is equal to f of say theta comma t plus epsilon. Say y is equal to e to the power minus theta t. The simplest nonlinearity. If it is there, let's see what is s of theta represents. You get summation u, where u is the number of observations, yu minus t of minus theta tu square into, okay, so this is u s of theta. Now, if you do delta s by delta theta, then what you will give do? This is u 2 yu minus e to the power minus theta tu, and there will be plus tu e to the power minus theta tu. Right? So this should become and it should be equal to 0. And this clearly shows this function is nonlinear. Correct? Involving exponential terms and x into e to the power minus x, kind of this. So these are all nonlinear equations. Okay. So once we have done this, question arises that all questions, whether we are trying to solve for linear models or nonlinear models, our main task is or aim is to find out the parameters, to estimate the parameters, the unknown parameters, which we call, okay, to estimate the parameters. In this case, it is an iterative process. So I will give you a brief introduction, okay, that how to estimate the parameters, and we will stop here because not much questions, as you can see in the assignments, is not involving this particular part. However, the concept is very important. One must know. All right. So what we will do here is that for this kind of estimation of parameters in the nonlinear estimation model, we use very famous called Taylor series expansion. So what we do is that suppose f of x around the point A can be written as f of a plus f dash a upon 1 factorial x minus a plus f double derivative at x is equal to a divided by 2 factorial x minus a whole square, and so on. It will go on. Okay. So based on this Taylor series expansion, we'll try to do the estimation. Okay. So in the beginning, as you can see, it's an iterative process. There must be some kind of a starting point. Okay. So and we are estimating what? The parameters, theta. Okay. So the starting point is like this: theta 1 0, theta 2 0, and so on up to p parameters, right? So theta p 0 be the initial values of parameters. Which parameters? The actual parameters like theta 1, theta 2, so on up to theta p. For all these parameters, let us say that the initial values we know, and these are this. You can guess also, fine. Okay. So the initial theta vector can be written as like this: theta 1 0, theta 2 0, whichever way you can do. Okay. So this is your matrix or a vector. All right. Next, we go for the actual equation u tilde theta tilde will be what? Apply the Taylor series expansion about this. Okay. So apply, let me write here, apply Taylor's expansion about theta not tilde. So what will happen? It will be tu tilde theta not tilde, because we are applying about this point, like we have applied about a, plus summation. Of course, why summation? Because there are three parameters, so there will be three differentials. Okay, so it will be delta f divided by delta theta I, because there are I parameters. Again, f will be tu tilde theta not tilde. Remember, okay, or you can write theta tilde. This, oh, let me just erase it and write it. Space. Okay, so let me again write. So f of tu tilde theta tilde about f of tu tilde will remain the same, but this will be theta not tilde plus summation, of course, for all the parameters delta f by delta theta I tu tilde theta tilde at, so this will be also I, where theta I is equal to theta I 0, right? Into theta I minus theta I 0. Because ultimately you are performing the Taylor series expansion about theta 0. So theta I 0 will be the reference or ith parameter. And we have assumed all the parameters. And also assume that the higher order terms are 0, neglected. So remember here, higher order terms neglected. Okay, so this is how you can write. Okay, so you are what you are doing. You have started with some kind of an initial values of these parameters like theta 1 0, theta 2 0 up to theta p 0. Now what happens? You have created a vector for that. Now you apply the Taylor series expansion because you are actually estimating the parameters using iterative process. So you have an initial point and then you are estimating through Taylor series expansion. So writing this f of this function tu and theta tilde about these initial values. So it will be tu tilde theta not tilde based on these vectors plus summation will be there because there are p parameters and each and every time this f has to be differentiated with each and every parameter. So one will be, if you remove the summation, it will be like delta f by delta theta 1 plus into theta 1 minus theta 1 0. So let me write it. That will be easier for you. So it's just like f of tu tilde or theta not tilde. This is fine. Plus, it is actually meaning that delta f by delta theta 1 at theta 1 is equal to theta 1 0 into theta 1 minus theta 1 0 plus delta f by delta theta 2, the second parameter, theta 2 is equal to theta 2 0 into theta 2 minus theta 2. Like that way, we'll continue for all the parameters where delta f by delta theta p is equal to theta p 0 into theta p minus theta p 0. This is how you can write. This is what it means. All right. So this is done. Now we will just reduce these expressions. That's all. We are not change anything. Just reduce expression. See this. You are writing this as u tilde theta not tilde. Same thing. Just writing at this. Symbols are different. Beta I 0 is theta I minus theta I 0. Next, Z I U 0 is delta S upon delta theta I tu tilde theta I tilde at theta I is equal to theta I 0. Okay. So now once we have reduced up to this, we can short, in the short form we can write this as this is equal to, just write this now because we have reduced this expression, plus this will be summation I going from 1 to p Z I U 0 beta I. That's all. Okay. Finally, this is what? This is nothing but y of u, the response, which is equal to f of u theta tilde plus epsilon u, which this is the general form, which we have written earlier. Okay. So you can write yu as this minus fu of 0. Okay. That is equal to summation I going from 1 to p z I u 0. You can do like this. Absolutely fine. Okay. This into beta I 0 plus. So we can therefore estimate beta I 0 when I going from 1 to so on up to p by applying least square technique. So essentially, the nonlinear form is being linearized through the Taylor series expansion. That's all. Okay. So now your Z0 matrix becomes something like this. Z first parameter, first observation, and zeroth. Zeroth means the initial values. Similarly goes for Z pth parameter, first observation, zero. Go ahead. It will be Z of first parameter, nth observation with zero value. And this will be Z of P nth observation with zero. That's all. Clear? So this is done. Next is beta naught vector, which will be beta 1 naught, beta 2 naught, and finally beta 8 naught. And y0 is again a vector, which will be now y1 minus this, so on to yn, fn. That's just solve it. You know how to solve it. So it will be just write this as b naught or beta naught tilde hat, which is, this is now z naught transpose z naught inverse z naught transpose y. This is how we find the estimates. Now, once you find, this is the first estimate based on the zero values, the initial values. Okay. So bi of 0 is nothing but, we know that this theta I minus theta I 0. Why? Because there is nothing but beta naught. Okay. Now, next iteration. So the next iteration will be, so this is based on initial value. Correct? Next iteration will be theta 1, that is equal to, so this will be theta I1, which is equal to theta I0 plus bi0. Okay, so this is what you have. So this is the ith parameter, but this is the zeroth for the zeroth one. So this is for the initial, but this is for the first iteration. Remember, don't write like this. Let's write like this. Theta I of 1 is theta I0 plus bi0. This one is for the first iteration. And this is how you continue. And continue till what? So you started with theta I0 and estimated bi0. Okay. Now after say jth iteration, your theta, I will write j plus 1 here of the ith parameter is theta j plus b j, something like that. And you have to go on till your theta I of j plus 1 minus theta I of j is less than some tolerance limit delta, which can be say 0.0001, whatever. Okay, so you have to do like this. This is I, okay? This is the ith parameter of jth iteration, remember. So this is how you have to solve for the estimation of the parameters in case of a nonlinear estimation model. Okay, so this is the technique. Very similar to that of the linear regression model. And how we are getting into that is because of the Taylor series expansion. That's right. Okay, so we can stop here with all the concepts covered. Now we can go ahead with some questions, practice questions we can do and finish our. And for the next say 45-50 minutes, we can do something, some questions. Okay. So we will solve particularly some questions related to simple linear regression model and multiple linear regression model. Because these are the basic concepts. Other things like multicollinearity, dummy variables, these are all some concepts, of course, that you need to understand. But finally, when you apply, you have seen that most of the times these are the two fundamental concepts which we are using. Okay, so let us do some questions related to the simple linear regression model and multiple linear regression model so that the basic is clear. Now, if you go ahead with multicollinearity and all those things, you will be able to understand everything and solve questions. Okay, so let's start. Just a minute. So let's start. So suppose question is that suppose we fit model y is equal to beta x plus epsilon. You can see that it is a model where you have one unknown parameter. You have not used the beta naught. So it's a no intercept equation. Okay. Question is that find least square estimate of beta. This is the question. Okay. So let's solve this. So what you have is y is equal to beta x plus epsilon. This is the model which is given to you. What you need is the least square estimate. For calculating the least square estimate, what you do is that you take y hat is equal to beta hat x. Epsilon we don't know. Correct? So this is your least square estimation model. What next you do is that to calculate the least square estimate beta hat is to go for S's residual, that is sum of squares of the residual. So EI square, where I going from 1 to n. Fine. So let's do it. I goes from 1 to n, and this will be yi minus y hat I, that is beta hat xi square. So S becomes therefore summation. I'm writing now I yi minus beta hat xi square. Okay. Let us now, because we have to minimize the error. So delta S by delta beta hat is the next thing. So 2 summation yi minus beta hat xi. We are differentiating with respect to beta hat. So it will be minus xi. That should be equal to 0. One normal equation because one unknown parameter. So 2 into minus 2 you can remove. So you can write therefore xi yi minus summation beta hat xi square is equal to 0. All the summations in terms of I. Therefore beta hat will be summation xi yi divided by summation xi square. Right? So this is your least square estimate beta hat. All right. So this is how you can calculate. Next question is, next question, the expectation of least square beta, expectation of least square estimate actually beta or beta hat is. So how will you do it? You have your expression of beta hat. So solution is that beta hat we know is summation xi yi. So it's a continuation question. Okay? So don't need to worry. So this is your beta hat. What you need to find is the expectation of beta. So what you will do, just put the expectation on whatever the expression you have found. And after that, what concept you will take is that here in this case, x's are not a random variable. Only y is the random variable. Just use that and property of this expectation value. You can see that you can write summation xi is gone e of yi, and the denominator is completely a function of x. So you don't need to change. Now, what is the expectation of yi? Okay, let's write yi, which is equal to beta xi plus epsilon I, right? Now, if you take expectation of yi, what will happen? Expectation of beta xi plus expectation of epsilon I. We assume that epsilon I comes from n0 comma sigma square. Therefore, E of epsilon I is equal to 0. Put this equal to 0 and you write. So, E of yi, both are constant. Beta is constant, x is not a random variable. So, this will be beta into xi. Correct? Put this in the main equation. So, E of beta hat thus becomes, this is summation in I, this is xi. Now, E of yi can be written as beta xi. In the denominator, xi square. So, finally, beta can be taken outside. This is summation xi square divided summation xi square. Chop this, what you get is beta. So E of beta hat is beta. What does that represent? That beta hat is an unbiased estimator of beta. Right? This is done. Fine. Next is we have a data set and look at the question. This question will make everything in use. Next question is you have a data set. Let me write the data set. So this is X, this is Y. Okay. So this is, let me write 4.7 Let me quickly write it. Okay, there are 12 observations. Right. Let me write the y values. All right. So this is the data which is given. And the question corresponding to this is that find 95% confidence interval of mean value of y, mean of y, if x corresponding to that is 4.9. So you can see that this is the question. For any confidence interval, you need MS residual. You know that in case of simple linear regression model, because this is a simple linear regression, right? Linear regression model because one regressor is present. So you need to find out beta naught, beta 1. Then you have to find out SS residual, MS residual, and then go ahead for the other things. Okay. So this question means that you have to calculate all these things. So let us first fit the model. So let's take the solution that let us first fit the model. Since it is a linear regression in one variable, one regressor variable is there, so it will be y is equal to beta naught plus beta 1 x plus epsilon. So its estimation will be y hat is equal to beta naught hat plus beta 1 hat. So we need to find beta naught hat and beta 1 hat first. Okay. So for beta naught hat and beta 1 hat, there is for the simple linear regression model, there is a simple formula. Beta 1 hat, the slope can be calculated like this: xi minus x bar into yi minus y bar summation I divided by summation I xi minus x bar square. This is how you find out beta 1 hat. And what about beta naught hat? It's simple: y bar minus, once you calculated the beta 1 hat, into x bar. This is your beta naught. Simple formula, but you need to do some calculations. Like the xi minus x bar is what, yi minus y bar is what. Okay. So let me write down here that the value of x bar, if you calculate, so x bar comes out to be 5.3 and y bar comes out to be 5.16. Okay, you can check. And let us do one thing. Xi minus x bar you write as a part of a solution, and y minus y bar also you calculate. Okay, so if you do it, x bar we know, y bar we know. So each individual term you have to subtract. So let me just write it. I have already calculated. You will have calculator, so you can easily calculate. There will be scientific calculator provided in the examination hall, in the computer screen. So minus zero point 0.6, then again zero point 0.6, okay, minus 1. That's all. Next is y minus y bar is somewhat minus 2.16 minus 1.16 minus 0.16 4.84 because as you can see this is 10 minus 3.16 3.84 minus 2.16 1.84 0.84 then 0.84 again and minus 1. That's all. So these are already calculated. Now it's easy. Okay. So you can calculate the xi minus x bar into yi minus y bar. So what you will do is that you multiply each and every term like minus 0.16 into minus 2.16 and write it somewhere and then add. So if you now calculate based on the values which I have provided, this gives you, or let me write, this becomes xi minus x bar into yi minus y bar. This comes out to be, if you add some, becomes 10.5. And the denominator, x minus x bar whole square, it comes out to be 2.1. That means if you square each and every values of this row and add it, then you will get 2.1. Okay, so beta 1 hat as per the definition, it will be 10.5 divided by 2.1. What it will give? 5. So beta 1 hat we have found out. Beta naught hat is 2. So it is y bar 5.16 minus beta hat 5 into x bar which is 5.3. This gives you minus 21.34, right? Therefore, our fitted equation becomes minus 21.34 plus 5x. That is our fitted equation. Alright, once we have found out the fitted equation, the next thing we will go for is the ANOVA table. Because this will help you to understand that what is the degrees of freedom and all those things. Okay, so let's write the ANOVA table. Sources, degrees of freedom, then SS, sum of square, and your MS residual, mean square residual. Okay, so first thing is the regression, next is the residual, and next is the total. Correct? For the regression, only one regression variable you have. So there will be one regression degree of freedom. But what about total? S is total. This has degrees of freedom always n minus 1. So since n is equal to 12, this will be 12 minus 1, which is 11. And residual degrees of freedom is either you can do 11 minus 1, it should be 10, or 12 minus 2. Because two unknown parameters, so 2 degrees of freedom will be gone. So n 12 minus 2. Right? So this is clear, I guess. Now, next is to calculate the SS. So what is SS total? Is summation yi minus y bar whole square. So what you have to do? You have to take individual term here, square it and add it. Once you do it, it comes out to be 69.67. So you can easily write this as 69.67. Well, next is SS regression. SS regression, there is a very simple formula for SS regression, which is beta 1 hat square into SXX. What does that mean? Beta 1 hat square into summation xi minus x bar whole square. We have already calculated this. Beta 1 is also known. So 5 square means 25 into this is 2.1. Comes out to be 52.5. So you can write this as 52.5. And the last is the effect residual, which you can calculate from this formula SS total minus SS regression. So this is 69.67 minus 52.5. So how will you get it? This comes out to be 17.17. Okay, so this is how you can do. So this is easy to remember. So for simple linear regression model, remember this is for simple linear regression model. So calculate SS regression, calculate SS total, and you find out. Okay, so this is one of the ways to calculate. So you just write it here, 17.17. Okay, now what is the MS residual, mean square residual? So MS residual is, as per the definition, SS residual divided by residual degree of freedom, which is 10. We have found out. So it is 17.17 divided by 10, which is 1.717. So you can write it here, 1.717. What about this? 52.5 only. Why? Because 1 degree of freedom. That's all. Okay. Now what we generally do, let us do it. It is not being asked here, but let us just quickly do it. That is the significance test. Whether the beta 1 we estimated and the beta naught we estimated, are they really significant or not? So for that, we generally do this thing that beta naught or beta 1 is equal to 0 and h1 beta 1 is not equal to 0. Okay, at some 5% significance. We test it. Okay, so what is the test statistic? E is beta 1 hat minus beta 1 actual parameter, population parameter, root over ms residual divided by sxx. Okay, at h, which is beta 1 equal to 0. So if beta 1 equal to 0, just remove this as 0. So now test statistic become 5 because beta 1 hat we have calculated to 5. This is 1.717 divided by 2.1. All these things are calculated. This gives you 5.52, which is to be compared with T of 0.025 because T statistic is a two distribution, it has a two-tailed distribution. So 0.05, 5% means 0.05 divided by 2, 0.025, comma 10. So 5.52 is much greater than 2.228. This value is 2.228. So it is significant at 5% level. Then next is for the beta naught. So H naught, that is beta naught equal to 0. H1 is beta naught not equal to 0. Same. Now the test statistic is beta naught hat minus beta naught, the population beta naught. Root over, there is some change, ms residual 1 upon n plus x bar square divided by sx. This is how the parameter is written. Okay, at h naught again, that is beta naught equal to 0. This goes, t becomes therefore is minus 21.34 divided by root over 1.717, 1 by 12 plus 5.3 square divided by 2.1. So once you calculate all these things, you get minus 4.44. So mod of t, which is nothing but 4.44, is, we have seen, it is greater than 3.025, comma, what is the degree of freedom? 10, right? So which is 2.228. Therefore, beta naught hat is significant. Alright, so this is the next. Another thing is the coefficient of determination. Let's do it and then we will come back to the original question. Coefficient of determination. So I am trying to cover as much as concepts which are related to the simple linear regression model so that it's a good revision. Okay, so this is nothing but r square, which is 1 minus SS residual divided by SS total. We have all the values, just put it and get the result. 0.75. So you can see that it's a very good model because 75% of the variance of y is being explained. All right. Now let's come to the actual question, that is confidence interval of mean response. That is what is said. Mean response y at some value of x. So given e of y is suppose e for x is equal to x naught, which is equal to 4.9, and e hat is the estimated response, that is y at x is equal to x naught, is y hat. Okay. So this becomes minus 21.34 plus 4.9, this is x naught into 5. This gives you 3.16. We know that the confidence interval is E hat plus minus T of the level of significance alpha by 2 n minus 2 root over ms residual into 1 upon n plus x bar minus x naught whole square divided by is x6. That's all. Okay, so let us see x bar minus x naught, which is 5.3 minus 4.9, which is zero point 0.4. So as you can see, the second term is very, very small. So 3.16 E hat plus minus 2.228, because 95% is the same value, into, if you put all the values, it comes out to 0.2739. So it will be 3.16 plus minus 2.228 into 0.5234. So it will be 3.16 plus minus 1.1166. So the confidence limit will be 2 comma 4.32 approximately. Okay, so this is your thing. Okay, also just for the beta one, the confidence limit becomes this. I just write it down. You all have these things. You can easily do it. Ms residual upon s equal. And for beta naught, it is beta naught hat plus minus e alpha by 2 n minus 2. Same ms residual, but n by n plus x bar square divided by f(x). That's all. Okay, so positive, the higher value is the upper limit and the lower limit is the lower values. So this is related to the simple linear regression model. Okay, and let's now move towards another question related to the multiple linear regression model. So everything is solved. I have solved everything. So what essentially needs to be done are the formulations that you should remember. So let us quickly do that uh, question and let's stop the session. All right. So let's write the question. This is x1, x2. This is one of the practice questions, uh, which I think I have forgot to solve. So I'm solving it right now. So 190. This is 35. Let me write it quickly. Then we'll solve. There are, I think, 16 observations are there. 175, 294.3. Next is 156, 218, and 44.3. Finally, you have 190, 220, 83.3, 178, 210, 91.4, 132, 208, sorry, 43.5, and 148, 225, 51 point. That's all. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 observations. So n is equal to 16. Okay. There are 16 observations, two regressive variables as you can see. So question is that, of course, fit the model. What is the model therefore here? Is beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. So of course find the estimators beta naught, beta 1 and beta 2. So easy, you all know this, just a practice one. So let me just, instead of writing the X matrix, you know that X matrix how to write. Just I will say that if X is, there will be your 16 rows and 3 columns. One with all values of 1, next is x1 and next is x2. So just if I write like this, it will be all 1 and this will be x1 and this will be x2. So it's 16 by 3. What about x prime? This will be x prime 3 by 16. So if you now multiply matrix multiplication x prime x, what it will be? It will be a 3 by 3 matrix. Correct? Because as you can see, right? Because x prime x you are doing. Therefore, x prime x inverse also will be a 3 by 3 matrix. Right. So let me, I have calculated the x. It's a bit tough calculation. Means a lengthy calculation, not tough, but lengthy calculation. You have to calculate determinant, then adjoint, and then you have to calculate. Okay. So let me just write down. I think the questions, if it does not allow any kind of programming, if you allow only the scientific calculator, then I think the number of observation will be less and it is easy to calculate the inverse and all those things. Definitely. Okay. So don't worry about that. So 13.12094 minus 0.02013 minus 0.045797. Okay. Minus 0.02013 minus 0.045797. This is 0.000121 and this is 1.217 to 10 to the power minus 6. This is also same. As you can see, this is a symmetric kind of a matrix. And finally, this is 2.14 into 10 to the power minus 4. So it's a 3 by 3 matrix. Another calculation is x prime y. So what it will be, of what matrix order it will be. See, this is 3 cross 16, and this is 16 cross 1, so this is 3 by 1. So 3 rows will be there. So if you calculate, it comes out to be, that's all. And you need these two things only to calculate the estimators, beta hat. So what is the formula? X prime x inverse, x prime y. All right. So just put it and you get the result beta hat as minus 67.88.90608 and minus 0.0642. So y hat is minus 67.88 plus 0.91x1 minus 0.0642 x. That is the estimated model. So now let us go ahead with this and write the ANOVA table. Okay. ANOVA table, and finally we will do some significance testing and all. And we can then, I think, leave for today. So yeah, let's do the ANOVA table. So as you know that there is some source, there is degree of freedom, then SS and MS. So what are the variables? Regression, residual, and total. Okay, fine. For the degrees of freedom of the total, what it will be? You know that for the SS total, which is this summation yi minus y bar whole square, its degrees of freedom is always in minus 1. Why? Because there is only one constant. The summation yi minus y bar is equal to 0. That is the only constant. So it will be n minus 1, that is 16 minus 1, which is 50. Right? Regressor, there are two regressors, therefore 2 degrees of freedom. And what about the residual? 15 minus 2, 13. Right? So let's go ahead and calculate the SS values. So SS total, this thing can be further written as, if you just open the bracket and you will see that it will be like this. Easy form, right? So this can be written. Remember, the SS regression formulation is beta hat prime x prime y minus n y bar square. And SS residual is y prime y minus beta hat prime x prime y. These three formulations you should remember, okay, to easily solve the questions. Okay, so let's calculate then. Let us see this one, beta hat prime x prime y, because in these two it is equal. If you do this calculation, you will get this value to be 78580.86. Okay, let's see what is y bar. Easily calculate 66.98, 125, all are there. And summation yi square, let us do, that is 80 to 12.95. And this is nothing but y prime y. So it's same. Okay, so let's calculate each and everything. So SS total is what? Summation yi square or y prime. Yeah, so this is the 212.95 minus this 78. No, this will be n y bar square. So n is 16, y bar 66.98 square. So if you do it, it comes out to be about 8429.15. Okay, next is SS regression, which will be 78580.86 minus 71783.81. What is this? This is the uh, your beta hat prime x prime y. No, not this. This is n y bar square. This, if you calculate, it comes out to be this. All right. So this gives you, this is regression. This is regression. So this is 6797.05. And finally, as a residual, you calculate 7. So this will be, you can subtract it, about 1632.09. Okay. So this is Done. So you can write it here, all those values, just put it here. So we'll about 6797 is 1632 and about 8429 or something. Mostly equal, almost equal you can see. Now how to calculate MS residue? Just SS by 2. Here SS residual divided by 13. SS regression divided by 2. Okay, so this can be easily found out. Now if you be asked to check the significance of the entire regression, just use F statistic or you can use T statistic, whatever you want. But F is better. As you can see that if you have SS regression and SS residual, you can calculate these two and which it will be 3398.5 divided by 125.5. And what will be the comparison? F of 0.05, numerator 2 degrees of freedom, denominator 13 degrees of freedom. Already shown. This value is 3.81 and this value of F is 27.06, which is much greater than 3.8. Therefore, significant at 5%, right? So remember that you can always use T statistic because F is equal to T square. Fine. So once we have done this, one last question if we will do and we can end the session. So the question is, right, what proportion of the variability in Y remains unexplained? Okay, this is the question which is being asked. So what to do? Proportion of variability in Y can be only answered through coefficient of multiple determination. Okay, and what is the formula of that? R square is SS regression divided by SS total. Now, this is the coefficient of determination or multiple determination, whatever determination. Okay, this explains the variability in Y. Right. Now, if I write this R square as, I know that SS regression is nothing but SS total minus SS residual divided by SS total. Yeah. So it will be 1 minus SS residual divided by SS total. Correct? This we can write. Now, if I write now SS residual divided by SS total, this should be 1 minus R square. And if R square represents the variability in Y or explains the variability of Y, then 1 minus R square is the unexplained variability, right? Therefore, we can say that the unexplained variability in Y can be quantified as SS residual divided by SS total, right? So this is the thing which you need to calculate. We have already seen this. This is 1632 divided by 842. Roughly comes out to be about 20%. Okay, so this is the amount of variability not explained. That means 80% has been explained. Therefore, whatever the model we have found is a good model because at least 80% of the variability has been explained. So it's really a good model. Okay, so this is what the question are we have solved. So I think these are enough to stop today's session. Okay, some important and basic questions we have solved. We know that how to solve them. And there are different concepts of multicollinearity where you can see that this x prime x inverse will become unexist. Means it is, I would say that the columns of the x are linearly dependent. Then the problem of multicollinearity comes and we try to solve it by increasing the number of data, or there are many things like principal component analysis is there so that the correlation is removed. All those things we have discussed finally. So, and then dummy variable part comes, then comes whether the assumption which we have taken, epsilon is coming from a normal distribution, is it a right assumption or not? We have checked it using residual plots and all those things. Please check all those uh, lectures. And finally, dummy variables comes. Then we have discussed a lot about that. Finally, generalized linear model. When the y, the response variable, is coming from some different distribution. It can be easily solved using some link function, which we have discussed in the last class. That through that link function, when we can solve through that link function, when the given distribution is of a canonical form and belongs to an exponential member of family. Okay, so if this condition satisfies, then we can go ahead with the link function, different link functions. Okay, so today we have solved these two questions, which are basic questions, important. Okay, and also try to give you the basic brief introduction about the nonlinear estimation model, how to solve with estimate the parameters using iterative processes. So that's all, and we have solved the assignment. So all the assignments are already solved. I've tried to solve it. Okay, so with this, I think I can end the session. So this is the last session which we have. Okay, okay, all the best. Thank you.